Hello everyone and welcome back to Math with Vansh. In this video we will be continuing with Unit 1 of the AP Calculus curriculum, which deals with limits and continuity. So if you're ready, I am too. Let's get started. Now just to recap, let's go over what we did in the previous video. In the previous video we defined what a limit actually is. Now the formal definition of a limit is when a function gets arbitrarily close to a y value as x approaches a certain x value. Now what does that mean? The word arbitrarily basically means really, really close, or even infinitely close, but never actually at that y value, okay? So when x approaches that value c, the function gets arbitrarily close to a certain y value, and that certain y value is going to be your limit. Now it's important for a limit to exist, and a limit exists only when it approaches the same value from both the right and the left. Now limit notation is notated as LIM as x approaches a certain x value, c of f of x, the function, equals L. And L is going to be your certain y value, right? And for this to exist, both the limit as x approaches c from the right or from the positive end of the function has to be equal to the limit as x approaches c from the left or from the negative side of the function. And only then will the limit actually exist. Now in this video, we will be focusing on how to solve for a limit. There are three main ways to solve for a limit. The first is the numerical method. The second is the graphical method. And the third is the analytical or algebraic method. So in this video, we will only be covering these two methods because the analytical or algebraic method requires its own video. Okay, to start off with the numerical method, we have a table. Now this is basically what the numerical method is. It's using a table to evaluate limits. So for example, we have the limit as x approaches 0 of x over the square root of x plus 1 minus 1. And we want to find out what this equals, right? So we have a table of given values here. And you can see that x equals 0 is right in the middle right here. And we have values getting closer and closer to that x equals 0 value. And notice how it's coming from both sides, from both the negative end and both from the positive end. Now this is what I mean by limits from the right and limits from the left. This is a limit from the left, and this is a limit from the right. So as you can see, these values really get arbitrarily close to 0. It's not like 2, 1, or like 3, 2, 1, 0. No, it's really small numbers that get almost infinitely close to 0, okay? So we have these values, and we can see that negative 0.01 is 1.99499, and then negative 0.001 is 1.99950. And then from the positive end, we can see the same thing. We can see that 0.01 is 2.000499, and 0.001 is 2.0050. Now, if we try to plug in 0 into this equation, we see that we get 0 for x over root 0 plus 1 minus 1. And then this is equal to 0 over root 1 minus 1, which is equal to 0 over 0. Now, 0 over 0 is undefined, which is why we can't just simply plug in this value. And that's why we're taking the limit. So back to this table, we can see that as the values get closer and closer to 0 from both the left and the right, these values seem to be getting closer to what value? Well, we can see that these values are really close to 2, but right below it. And these values are really close to 2, but right above it. So we can say that it's safe to assume that the limit of x as x approaches 0 of this function is 2. And we can say this because the limit as x approaches 0 from the negative end, from the left, of this function f of x, we'll call this f of x right here, we can see that this equals 2 because it approaches 2. And same thing on the right here, we can see that the limit as x approaches 0 from the positive end, or from the right, of f of x also equals 2, because these values also seem to be getting much closer to 2. And because both the limit as x approaches 0 from the left and the limit as x approaches 0 from the right both equal 2, we can say that the limit of x approaches 0 of f of x equals 2. Now, just to be safe, we have another example. We have the limit of as x approaches 2 of x minus 2 over x squared minus 4. And we want to know what this equals. And again, we have a table of x and f of x, and we can see that there are values getting arbitrarily close to 2 from both sides, from the negative side and from the positive side. Okay? And we have our values. Now we can see that as x gets closer and closer to 2 from the negative side, these values 0.2564, 0.2506, and 0.25006, they seem to be getting closer to 0.25. So we can safely assume that the limit as x approaches 2 from the negative side, as x approaches 2 from the negative side of f of x equals 0.25. Okay? And now same thing from the positive end, or from the right, we can see that as x gets closer and closer to 2 from the positive end, these values 0.2439, 0.2493, and 0.2499, they also seem to be getting closer and closer to 0.25. So we can see that the limit as x approaches 2 from the positive end of f of x equals 0.25. Okay? And now, since both of these values are equal, both the limit as x approaches 2 from the left and the limit as x approaches 2 from the right, since they both equal 0.25, we can say that the limit as x approaches 2 from both ends of this function is 0.25. And this is basically what the numerical approach of solving a limit is, but this can be kind of tedious at times, making the entire table and all that. So let's look at a different way to find a limit. Now, for the graphical approach, we have the same function, x over root x plus 1 minus 1. This is the same function we used in our first example for the numerical approach. And again, we have the limit as x approaches 0 of this function. Now, we have this function graphed over here, and we can see that when x equals 0, which is what we're approaching to, we can see that there's a hole. And this is, again, because if we plug in 0 into this function, we get 0 over the root 0 plus 1 minus 1 equals 0 over root 1 and then minus 1, which is just 0 over 0. So that is an undefined value, so this is why we have a hole in the graph at that value. So to find this limit graphically, we can just kind of see where the graph seems to be approaching from both the right and the left as we get closer and closer to 0. So from the negative side, or from the left, this is going to be from the left, and we can see that this value seems to get closer and closer to 2 right here. So we can say that the limit as x approaches 0 from the left of f of x equals 2. And that's if this is f of x. And same thing from the right, if we get closer and closer to 0 from the right, or from the positive side, we can also see that the graph seems to be approaching this y value of 2. So we can also safely assume that the limit as x approaches 0 from the positive side of f of x equals 2. And since both the limit as x approaches 0 from the left and the limit as x approaches 0 from the right of f of x are both equal and both equal to, we can say that the limit as x approaches 0 of this function equals 2. And if you remember, this is the same value that we got in our previous example in the numerical approach. Now for our last example, we have a piecewise function right here, which I have graphed. We have f of x equals negative x to the third, which is right here, as x is less than negative 1. 2 if x is between negative 1 and 4, inclusive of 1, which is why I have the closed dot and open dot right here. And then root x if x is greater than 4, which is right here. And we want to find these two limits. We want to find the limit as x approaches negative 1 of f of x and the limit as x approaches 4 of f of x. So if we look at this graphically, we can see that the limit as x approaches negative 1 from the left or from the negative side, the limit as x approaches negative 1 from the negative side seems to be about 1 right here. And we can see that the limit as x approaches 1 from the positive side, so from this side, we have to look at this graph, at this line right here. So, and we can see that this seems to be 2. So as we approach negative 1 from the negative side, we look at the x cubed function, and that approaches 1. And from the positive side, we look at the straight line of 2, and that approaches 2. So since these two values are different, they do not approach the same y value. So we can say that the limit as x approaches negative 1, sorry, this would be negative, as x approaches negative 1 from both sides does not exist because both of these limits are not equal. So this does not exist right there. Okay? Now if we look at the limit of f of x as x approaches 4, from the negative side, we can see that the limit as x approaches 4 from the negative side of f of x equals, if we look at this graph right here, from the negative side, x equals 4 is right here. So about right here, x approaches 4, it seems to stay on that line of 2. And the limit as x approaches 4 from the positive side of f of x, now we're going to look at the square root function right here because it's coming from the right or from the positive side. So we look at this function, and this also seems to be approaching the same y value, 2. So because both of these values are equal, and since they approach the same y value, we can say that the limit as x approaches 4 of f of x is 2. And that's basically what the graphical approach is. It's basically just graphing a function and seeing what the function approaches as you get closer and closer to a certain x value. So that is going to be it for this video. We covered how to solve for limits graphically and numerically. And in the next video, we will be covering the properties of limits and how to solve for limits algebraically. I hope you found this video helpful, and I will see you for the next one. Bye-bye.